So, thank you everyone for being here. In my presentation, I will present to you some of the results that we've gotten in the exploration of the transformer architecture. In particular, we are exploring the necessity of the weights of the queries, keys, and values, which, as we all know, are a building block of the transformer and of all the current state-of-the-art LLMs and chatbots that we might come across. So, first of all, let me repeat this, that this is still work in progress. So these results are not final. There are still many things to do. And you're kind of following the half-baked cake here, or having a taste of a half-baked cake at the moment. So I will give a fast overview of the decoder-only transformer architecture. We will define some mathematical language that we thought could be useful in understanding of the transformer. We will give our intermediate conclusions that we've had using this mathematical language, so a bit of theory, and then the practical problems that we've faced, as well as finally the further steps that we, of course, would like to take in order to improve the results and to really see if we can reduce the number of parameters of the transformer architecture. So, again, the goal of the presentation is to understand the attention mechanism in a sense by questioning it. I've had a professor who once said that if you want to understand especially a mathematical statement, you need to start by questioning where does this statement fail, where does the conclusion of this statement fail, if any of the conditions are not satisfied. And in this case, we are kind of questioning the attention mechanism, in a sense, or at least one part of the attention mechanism. We will present again the ongoing experiments that are, you can consider them as in progress. And hopefully maybe there will be somebody interested in fruitful discussions on the topic and even collaborating on this to further the work. The goal of the work is, of course, to reduce the number of parameters in a neural network and give a mathematical framework that could be used in a better notation of the attention mechanism. So, as you all know, the number of, the neural networks, in particular the transformer neural networks, use a lot of electricity. They are very heavy. If you've tried loading them on your own computer, you've faced the problems of loading the network. And our goal here would be to kind of reduce the number of parameters by only 3 to 8%. You might say to yourself, 3 to 8% is nothing, but when you take into consideration that a training of neural network sometimes engages up to 100,000 GPUs, reducing at least the number of GPUs that need to carry the weights by 3 to 8% is not insignificant. Even more so, the amount of electricity is not insignificant. So let's start with the decoder-only transformer. What one has is the original transformer architecture. We take out the part where we have the embedding, the encoder layer of the transformer, and we are only interested in the decoder transformer. So the decoder part of the transformer. Again, this mechanism is being used by all the modern LLMs. So I think this started somewhere around the time of GPT-2, where OpenAI realized that they do not need this part here in order to create a chatbot. So we have the outputs. So basically, when you train such a network, you take a text. You take a text, you tokenize it. You create for each of the tokens, you create an embedding, and you create a positional embedding. By the way, the positional embedding is something that is really new to the transformer network. We had attention in RNNs that was, introduced prior to the transformer, but the fact that you add some coefficients to your token embeddings is some, relative to the position of where they land in the sequences is something that is very new. In the RNN architecture, this was not necessary because this sequentiality is kind of implied by the architecture. You know that you're in a sequence, and the model kind of gets prior information of everything that has happened, prior to the given token. So this was really not necessary. Whereas the transformer does everything in parallel. So having information of where each token stands is very important. So yeah, a little bit of a detraction towards this end. So anyway, this gets added up. The information from this layer gets split into 3 parts: the values, keys, and queries, and basically they get multiplied in this multi-headed attention. There are some skip layers and then some normalizations. This gets repeated a few times. We get a final layer at the end, and finally we output the probabilities for the next tokens. So for the next part of text that should come given the prior part of text. And as we know, the transformer model basically only predicts the next token. So basically one can think of predicting just the next word in a sentence. And it does this in a sequential way. So at each step, it just predicts the next word. There's no inherent planning of what it's going to say and then for it to be saying it. It just, speaks its mind as it thinks, in a sense. So the number of weights in a transformer layer is basically you have the number of layers of these attention layers in the middle. You have the input basically embeddings, and finally the output probabilities, kind of the same dimension as the embedding. So these are basically these two times the embedding dimension times the vocabulary size. That's basically, again, this layer here and this softmax at the end. So the linear plus softmax part. Next is everything that's in the middle. That has a dimension of, well, the number of parameters equal to the number of layers, of course. Then it's the embedding dimension squared, and then we have 4 plus 4, which are the linear layers, the MLP part, so the multi-layer perceptron part. And for the queries, values, keys, and the output projection, we count them only once because they transform the embedding dimension, so a vector of its size into another vector of its own size. So that's why the dimensionality here is only 1. And if we remove any one of these, we would get, depending on the architecture of the model, we would get from 3 to 8% of reduction of the total number of parameters. By the way, for anyone who is interested in this topic, there's a very good implementation that we even started from. That's Karpathy's Nano GPT. Basically, you have GPT-2 that you can implement from scratch and train it on your own if you have the resources. You can even train it on a 3090 GPU, especially with the new scaled dot product attention. So this is our starting point here. And again, our idea is to remove one of these matrices. At least one of these matrices here, one of these 3. We will introduce a bit of mathematical language that could potentially help in the understanding of the self-attention dot product. Again, this is nothing exceptionally new in the sense that this language exists and these things have been already written in a different way, which might be more useful to some people. We thought, why not try some other language that might help with the calculations. So the attention mechanism, the usual way of writing down the attention mechanism is using these formulas. You have your embeddings of your tokens. This is your X matrix that carries within each row the embedding of each token. The queries and keys and the values are linear transformations of your inputs, in a sense. And finally, your multi-head attention is basically a concatenation of all the attention heads, and then all the attention heads are multiplications of the queries, or basically multiplication. There should be actually X here. So X times WQ, X times WK, X times WVI. And you also need to put the softmax on top of each of these, on top of this product here, and then multiply that by the values. So yeah, here it should be just the query key value without the weights. And another thing that we will use is the Adamar, or just the simplest way in which you can multiply two matrices, vectors, tensors, whatever. It's basically the element-wise product. So the first element gets multiplied by the first element, second element, and so on. And with this type of notation applied to matrix blocks here instead of just elements, we found a faster way, in a sense, to write this down. Of course, this inherently implies other complications, but we thought, why not? So why not move from concatenation and other cumbersome notation into compact formulas that are already well developed? So we basically apply linear algebra of block matrices. Each matrix can be written as basically blocks or column blocks. For example, here the matrix W is written as block matrix of its columns. So these are the first, H columns, and then you have another block of H columns, and so on. So each of these matrices has the same dimension, U1 and so on, and W1 and so on. So they all have the same dimensionality. In the same sense, we can also write a matrix as its as row blocks. Basically, you just look at these chunks of the matrix V. Or in another sense, we can look W as a concatenation of all of these, U as a concatenation of this, and so on. And in that sense, we can kind of define a Adamar or pointwise product, where we basically just multiply the first block with the first block, the second block with the second block, third block with the third block, and so on. Or an inverted, in a sense, transposed product, where again we multiply the first column block with the first row block, a second column block with the second row block. So you can see this in the notation here. Of course, we have the softmax function just being applied, as you know, as in the attention model, with a mask, where we mask everything that comes after a certain token so that it doesn't, interfere in our training. And we can apply this on a row level, or on a row level, and we can call this function as a causal softmax because it's basically, it's implemented in the causal attention layer. So why not just call it causal softmax? And in this sense, we can write the attention mechanism in this format here, which is much more compact, and you kind of can put everything into just one line, which, in my opinion, at least when I was writing this, it seemed to ease things a bit, at least in the sense of typing on the keyboard. So yeah, we kind of shorten down the write-ups of calculations, and this is useful in a sense. Finally, we have the scaled self-attention dot product. We can write it down as these matrices of X times the weights for the queries, weights times for the x times the weights for the keys. And finally, we can get this concatenation of these matrices, which are exactly the attention dot product. As you can see, I mean, with basically we get this here. Again, at least in my opinion, much more compact notation. And we can, instead of looking at two matrices x and y, we can just restrict ourselves to a single matrix xx here. So in a sense, a quadratic function. The idea here is to kind of remove one of the weights, as we said. And we arrived at a proposition that in a simplified transformer model, where you have just one layer without the what's it called, the layer norm or the skip connections, you can actually select a basis or re-embed your tokens in such a way that you can write down this scale dot product in using only one matrix. So you only need one weight matrix to represent both the queries and the keys instead of two matrices. So it is here that we are gaining this. It is actually here that we're gaining these parameters, or kind of losing these parameters, to be more precise. And we of course structured this in a proposition, but I won't bother you with it at this moment, because you can read it afterwards if you're interested. So again, as an intermediate conclusion of all of this mathematical language, we came to the conclusion that we can replace at least one of these matrices, or we can remove one of these matrices with just the projections. So the queries can become just the first coordinate, the chunks of coordinates of xi, and the keys part will remain the same. So the keys will remain. In this sense, the queries will be just this original matrix of weights. So we're just basically again here slicing x into column matrices, column submatrices, or however you want to call it. This is the implementation of the causal self-attention by in the code of Karpati. So I mean, you can look at it if you will, and you will just notice our change is very small, and it is here. So first of all, the attention is the three attention matrices are kind of packaged together in one single chunk. They're done with one linear layer. Basically, it's this 2 times the configuration the 2 times of the embedding size, and prior it's 3 times to the embedding size. So basically, we're gaining that parameters, these parameters, exactly at this point. And how do we put this into code? Well, basically, instead of having the keys being a projection again of queries, keys, values, and so on. The queries become just the original x sliced in the same way that the queries would get sliced, but they do not need to get. So here x needs not to be changed and transformed into a new matrix. Again, this is the way in which we handle these things. and again, this is the only part of the code where we need to do any change at all. There are practical problems to this approach. First of all, I said that this approach was done, so the mathematical approach was done in the case of a simplified model. Again, when we investigate theoretically machine learning models, we always do some kind of simplification because we still do not have the tools to actually understand what is behind what actually is happening behind all of these models. We simply do not have the mathematics developed to do so yet. We've only reached up until some very simple models, so the full understanding of very simple models like, for example, the linear regression. But these are much more complex. Yeah, so the understanding is much more difficult. So the practical problems that we can see right away is, first of all, that in training the model, we have weight decay. So that's basically reach penalty. That's a regularization of your parameters to keep them close to zero, or relatively close to zero. To work that around, so in our model, to try to relax it a bit, we reduce the weight decay of our new model that we're trying to train, because at this stage, we're trying to kind of overfit with our new model and to beat the original model at any cost. And then we will start, we would like to start afterwards to add more regularization and so on for it to be, more, for it to be able to generalize better. The next thing is, of course, that the model is much more complex than a single multi-head attention layer. It contains many layers, skip connections, layer norms. I mean, so at the end of the day, we have the intuition, and we say, let's try it, and let's see what it gets. In some variations of the model, even the GPT-2 that we test on, the embedding and the layers at the softmax part, so here, so these weights here and these weights here are shared. So this matrix here is just a transpose of this embedding matrix here. So in the sense we have what's it called? We have a further thing that makes it more difficult for our model. Why? Because the change that we're doing here, the change of basis, basically means that we're changing the embedding. And if we change the embedding at the level of, if we change the embedding, we're also changing the layer at the final linear layer, which makes things much more difficult for our model to handle. So for this, we need to run a test of a transformer model where the weights are not tied between these two layers. And again, for some models, this is the case. For Phi3, for the Gemma model, we have this weight tying. For some other models like Mistral, the Mistral models, family of models, or the Llama models, Llama 3 models, there is no weight tying. So this is still useful in that sense. So yeah, again, to overcome these complexities, we allow ourselves to increase the embedding dimension by a bit. So because we're still kind of with less parameters than the original model, and if once we are able to reach this, to reach the same results with our model and the original model, we will be able to start modifying things to be able to reduce the dimensionality of the embedding size, if we're able to do it. And if we're never able to do it with more embedding dimensions, I mean, it means that our model will fail regardless, so there's no point in trying to further optimize, to further reduce the parameters. So there's that. On the part of the weight decay, why that becomes a problem is that weight decay will keep the matrices close to zero. If we look at the queries and keys on their own, we will see that the weights are really centered at zero. So their mean is zero, their variance is, their mean and the medians are zeros of the weights of the queries and of the keys. However, if we look at their product, we will see that they're not really centered exactly at zero. Even if they may seem that they are relatively close to zero, they're not exactly zero. So this is another difficulty that our model might inherently have because of the layer normalizations and the lack of parameters in the model, in the lack of parameters that can create such such phenomena. So we've run a test here, as you will see, and the test setup was is that we use GPT-2 and the Open Web Text, which is an open source version of what GPT-2 was trained on, closely following Karpathy's code. We're training on a very slow GPU, so this takes a lot of time. The idea is that we're trying to shortlist models that we want to test on a much more higher-end GPUs, because these cost money, of course. So, you know, it's a bit of a tough time for the technology companies. So we have to be save as much money as we can. And finally, what you will see here is less than 60K training steps. In Karpathy's example, we have 400K training steps. So this means that there's a huge difference in the number of tests that we've done here and how many tests we need to do in order for us to really reach a conclusion. So yeah, again, what you will see on the graphs that I will show afterwards, on the x-axis is the index of the step. Multiply that by 2 because we're collecting the information every second step. We do not collect the information of the loss on every step. And the error that we're tracking for now is the log loss, basically the cross entropy function, so that we can check if these two models can kind of learn the same things in an equally or almost equally same way. The difference between our model and the original model is less than 1% in the training steps that we've done, which is promising, but again, there's a lot more work to do here. So yeah, this is the variant that we've tested right here. So we will need to find the log loss and so on. We've relaxed the weight decay on the attention part. We've relaxed the weight decay on the embedding part a bit, and we've kept the weight decay on the multi-layer perceptron to be the same. The number of layers and everything is the same. The parameters, we're having like almost 1% difference in the number of parameters here, because we are moving the embedding dimension a bit in our test here. You can see the results on the training set. On the validation set, by the way, I have the validation set here as well. They're very similar. Basically, the validation and the training set give the same results on this model because this model is relatively small. So overfitting is practically impossible. We can see that both models are, you know, they have, if we track their slopes, we will see that both are kind of reaching the same point. Because at that start, our reduced model starts with worse values, we get that our model trains faster, at least in the long run. Whereas the full model trains a bit slower, but even then we're still not able to reach the same loss, unfortunately. And you can see the differences of the values in the cross entropy loss in both models. If you look the large picture, you will see that the difference gets lower and lower, but at the end, I mean, I stopped this recently because I had we didn't have the time before the presentation. So, but as you will see here, the difference kind of increases just a little bit here. So we decided, okay, we'll stop the count at that point because we can show that we have something that's good enough, at least for now. So yeah, there's that. And the further steps will, of course, be to develop more robust and faster tests. We're running a a test that's not optimized in the sense that we're training both models on the very same chunks of data, so that we can, in a sense, guarantee reliability. Because here, when we're doing that, we know that they've been trained on the same data, and that this result is as reproducible as possible. We could put some random number generators when sampling the data so that we can train them independently, one next to the other, even though the random number generators can differ between CPUs, between different configurations. So that's kind of an iffy part. Yeah, and we need to test a better subset of models. We want to test also a single head attention variant combined with our approach. So add an additional matrix, just the one small matrix, together with our original idea here, and see where that goes. We're planning on publishing the code regardless of the results on GitHub real soon. So if you're interested for it, please let me know, and I'll let you know once we do that. And of course, ideally, we would like to go deeper within the theory and write a scientific article about our experiments. So yeah, again, these would be some modifications. We would add one single query to the query itself. So we'll have a linear combination of X, or the cuts of X, and to that we will add a single query matrix, hopefully, giving better results, because this doesn't modify the number of parameters by a lot, but why not? It's just one step ahead of what we could try. And this grouped query attention paper has caught a lot of attention, so I mean, why not try to combine them? Mathematically, it makes sense also because we're kind of increasing the rank of the matrix this way. But I will not bore you with that. Finally, a special thanks to the R&D team. That, of course, I mean, they're not here now, but they all contributed, at least in some sense, to the experiments. So yeah, a huge thank you to them. And thanks to you for your attention. No pun intended. Are there any questions?
Hi. Short question. How much time did the training and testing took on that single GPU? On that single GPU, how much time did the training and testing took?
We can train around 4,000. We train around 4,000 steps a day, 4,000 to 5,000 steps a day.
In the whole process, how much time?
One 390 GPU, both models on the same GPU, so that we can have the same split of data.
How much RAM that GPU has?
24 gigabytes. And
one more question. How did you split the data set? How much percentage was for testing or for training?
The train test split is pretty, I mean, the test set is very low. It's like maybe even less than 1% of the entire data.
Okay.
Because this is a very large data. You don't need to split like 70 to 20, 10. You can really do a significant. You can do a good estimate of your precision or of your quality metrics, even with a small percentage of the data.
Thank you.
Thanks for the presentation. I just wanted to ask, when compared to the more, let's say, traditional neural networks, like MLPs, CNNs, or all the others, what are the most important hyperparameters, for example, when you optimize one LLM or one transformer? What are the, for example, in MLPs, I guess the learning rate or the optimizer that you use or the error. And here, what are the hyperparameters that mostly influence the performance of one LLM?
So thank you for that question. Let me get back to this slide. So in a sense, you can see these are the parameters that you're kind of looking into when working with the LLM. So the number of layers is a very important parameter. The number of heads that you will consider is also an important parameter, and the embedding dimension. So most of the weight, in the sense of how much memory your LLM will take, will be defined by the embedding dimension and by the number of layers. As well as there's another part here as well as the total number of your dictionary that I haven't mentioned here, but that influences your model a lot as well. However, I don't think that you will be modifying that a lot, since you would be using predefined chunkers of people who have already done the chunking. But you can save a lot of parameters there as well if you reduce the number of, in theory, if you reduce the number of possible tokens. Other hyperparameters that you will tune and you can tune is the weight decay. And if you're training a small LLM, as in this case, you can even do with a smaller weight decay. As your model grows, you will have more weight decay that you can add to it. Another parameter is the dropout. In the original paper, they use 10% dropout, but in the original paper, they also have a much larger version of the GPT-2. So they have 1 billion parameter GPT-2, which is it could potentially overfit, and having a dropout there could help. But in this case, in a very small LLM, you don't need any dropout at all. If your data set is large enough, let's say from, I'd say 10 gigabytes onwards.
And one more question here on this slide. The first variant or all the other ones don't use at all the matrix WQ, right? The one
Yes.
for Qs. Is there a way, for example, to somehow create a new matrix that would be a composition of the two matrices for the output and for the question, for example, or the keys or the answer, using some methods like PCA or SVD to decompose the matrix and then combine in a new one?
In a sense, that's exactly what is happening with the queries and the keys. They are a low-dimensional representation of a larger matrix, because their dimension, the dimensionality of the I do not have a pen here, but the dimensionality of the queries and keys matrices for each head is the embedding dimension times the dimension of each head. So here, for example, here, it will be 12 times 64 into 64 dimensional space. And that kind of, it kind of puts things into a smaller dimension, and then the keys puts things into a larger dimension. In a sense, you could put one matrix, but the idea between the queries and the keys is to have a smaller dimensional representation. So because what you're getting with the queries and the keys, for each head, you're kind of doing a low rank approximation of an original large matrix, and the maximum rank of that matrix will be 64. So the dimension of the head. So in a sense, you could, but there's no point in it, because you're kind of defeating the purpose of having multiple heads. If you do that, in a sense, you will have a mixture of models, because you'll have multiple. You'll have multiple big heads instead of multiple small heads. And the multi-head attention idea is to have relatively small heads. So, yeah.
Thanks.
You're welcome. And thank you.
While you were training the GPUs, did you have energy problems of some sorts? And if so, how did you solve them?
No energy problems. I was lucky, I guess.
How many GPUs did you train on?
One. This was done on a single GPU. So on a single GPU, I could get up to 5,000 on some configurations, 5,000 steps a day, which is not a lot, but yeah.
Do you know what sort of problems will come up if you scale it up even further? Like, I don't know, 1,000 GPUs or 100 GPUs?
Nope. To be honest, the Karpatis code is being trained on 800 GPUs. So, I mean, if it works for him, there's no reason why this code wouldn't work for that many GPUs. Training on more than that would be kind of unnecessary, because with the modern implementation of flash attention, the training is much faster than when it was implemented at first. So with 8 GPUs, you can do wonders. for this size. If things explode, of course, if you want to train a larger model, I assume that there will be other problems in the training that could arise. But you know, if you're training on many GPUs, I'm not aware of the problems that might arise. Sorry, I'm not aware how to handle the problems that might arise, like a GPU, you know, not crashing or something like that. So yeah.
Okay, thank you.
Кой следен или ја треба да одлучам? Повели тука па последи мене.
Thanks for the great presentation. I was basically wondering why is the weight tied between the embedding layer and the head layer? And a follow-up question to that, why doesn't this occur in Mistral and Llama 3 as you...
So why they tie the weights? It's to save. Where did I put it? Yeah. First of all, they do it to save space in the sense of the number of parameters. There were some experimental tests where they found out that it didn't change the outcome that much. So for smaller models where the number of parameters is very important, it is important to have a small number of parameters. Cutting that size is good enough in a sense. So they were. So they did that. And by the way, this has been done even prior to the transformer architecture. So the first weight tying between the embeddings and the language modeling head, the last linear layer, has been done even at the time of LSTM. So yeah, the idea is to save the number of parameters in a model, kind of being able to squeeze it into something smaller. And just a side note there, if you train such a model I mean, if you do inference with shared weights, you do not get much of a speed up, because you still need to do the multiplications of different type of information at the start and at the end. So it kind of only helps in you know, packing as large of a batch size as you can on a single GPU. And why some do not use that? I have it. Like Mr. and Llama 3, I think that they are very large models, and the amount of the percentage of parameters that is occupying the model comes from the numbers of layers. It starts to dominate, the number of layers dominates by a lot the number of parameters that are in this embedding layer. So it kind of becomes unimportant, and the results are of course better if you do not tie the weights. So I think that's the reason that in larger models like Mr. and Llama 3, they do not do that. The Phi 3, by the way, are pretty small models. The idea is for them to be small. So,
Great, yeah. Thanks a lot.
Okay, I have a question about the mathematical notation that you introduced in the middle of the presentation. Don't worry, I'm not gonna bother with the details. Just wanted to ask if the introduction of that mathematical notation led you to the potential discovery that you can remove one of the matrices, or was it the other way around, that you came to that, that you stumbled upon that possibility and then used that notation in order to prove that it's an actual possibility?
It started the other way around, in the sense that at first I noticed that here we have two matrices. As the other participant who asked the question said, you know, I saw that there are two matrices, and I started with the same idea. Why not just multiply this and have a single matrix instead of two matrices? And then I thought, but okay, you know, these are reduced parameters. How better can I do this, and what can I do here? And while thinking about it, and while trying to write things down in a you know, as simple way as possible, so that I could explain things to myself, I thought, you know, wait, we're just multiplying here, basically in the attention. I mean, actually here we're just multiplying for each part. We're just multiplying, you know, two blocks of matrices. Sorry, we're block multiplying matrices, and I thought, wait, why is this not used in the notation? Let's write it down that way so that I can, you know, juggle with it in a simpler way. Yeah. So, yeah, thank you.
HTEC.